Today we're going to look at two other equations that should be familiar from GCSE, the equations for power and the equation for efficiency. So let's have a quick reminder of what these things are. If you have a staircase that doesn't delete itself of a certain height h, and we have a person who for some reason is absolutely tiny compared to their staircase, and we move them across, they run up the stairs, they will do a certain amount of work. So the work is equal to the force times the distance. The force that's acting on this person they've got to overcome is their weight. So the useful work that we do in this situation is mgh. Okay? Now that in itself is unsurprising because we did it last time. However, another person who runs up and is much quicker does the same amount of work, but they do it in less time. That second person is more powerful because power is the rate at which work is done. Remember that work is just an energy transfer. Any form of energy transfer is work. Power is the rate at which that energy is transferred. It's defined by the equation power is equal to work done over time taken. And in terms of our units, the work done is the joule, the time we would normally work in is the second, and that gives us a unit of power, which is, I don't know why I've changed the colour of that one, but we have the watt, W-A-T-T. So it's a watt. So a power of 1 watt is 1 joule per second. If you want to know what a joule per second feels like, get something like your pencil case, lift it above your head, and that's about 1 joule. Doing that repeatedly once a second is a power output of about 1 watt. The watt, so the watt is equal to joules per second. That's a terrible sentence. Of joules per second. But in SI units, it will be, and first pause the video, see if you can work it out yourself, and we'll watch it is. So to get the SI units, we would go the power is equal to joules per second. The joule is defined by force. The joule is equal to a Newton's work force times distance. And the Newton is defined by mass times acceleration. So it's kilogram meters per second to the minus 2. So we can put that into there. So we get the joule as being kilogram meters squared seconds to the minus 2. And then we can put that over into there. And therefore that will give us the unit of power. The watt is kilogram meters seconds to the minus 3. If you want to have it in base units. Now, the other thing that you can do now is I've put an additional video just about James Watt because it's vaguely interesting. He was an engineer who developed the sort of he didn't develop the first steam engine, but he developed an improvement on the steam engine in 1776. And if you want, there's a quick additional video. It takes about 5 minutes. You can just have a quick watch on what it is that he did, because he revolutionised the world of work by developing a steam engine that was useful in the workplace. So have a quick view of that. So let's deal with some example problems. We'll keep them fairly straightforward. So number 1, let's deal with a weight of let's say 7.5 newtons is lifted with a power of, let's say, 30 watts for, let's say, 17 seconds. How high is it? Okay, so we have, to solve this, we've got, so power is equal to work done over time. We're lifting something directly up, so we're going to deal with work done is force times distance. We've already got it as a weight, not as a mass, so that's fine. So we're going to do 7.5 times height that we're lifting over a time of 17 is equal to our power output, so that's 30. And we can just rearrange. So height is equal to 30 times 17 over 7.5. And do I have a calculator? Yes, I do. I'm ready for this. 30 times 17 over 7.5. We have gone 68 meters. So that's pretty high. You know, we're not lifting a very big weight. So that's how we can sort of solve a problem of lifting. So there's very commonly this idea of when you go vertically, it's quite nice and easy. But let's deal with a second. So let's deal with a sort of slightly different example. I'm going to deal with one where we take a car, we've got an engine, and we're going to put our foot down and we're going to accelerate the car. And this wonderful car is going to go brum, 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 and that's fun. So let's I looked up some specs for a kind of a sports car-ish sort of one, like fancy one, the type that I'll never own. And this is what I discovered, is that it's got a mass, it's got a heavy car of 1,760 kilograms. It's got a 0 to 60 miles per hour time of 4.7 seconds. The question is, can we estimate the power of the engine? Well, turns out we can. Let's assume, because it's easier, let's assume there's no air resistance, and let's assume that all the energy of the engine, the power of the engine, is going to go into accelerating the car. So if we do that the work done from the engine is all going to go into the kinetic energy of the car. Now that's not true in things that are going at 60 miles an hour. There's quite a lot of air resistance and stuff we have to overcome, but we're going to ignore that for the time being because it makes the problem slightly easier. So what we want to know is, what is the final kinetic energy of the car? Well, we need to know really for that is, well, how fast is 60 miles an hour in standard units? So up 60 miles per hour is equal to 96 kilometers per hour. So not 96, 97, because I worked it out down here. Aha. So not 96, 97. So 97 kilometers per hour. We can then do a conversion. It's all there already. I don't know if I'm going to move this up here. And what this allows us to say is that 97 kilometers per hour, to turn that into meters per second, we have to do 97,000 divided by the number of seconds an hour, 3,600. And we get 26.9 meters per second. So the kinetic energy when it's traveling at 60 miles an hour is going to be a half times the mass, which is 1,760, times 26.9 squared. So 0.5 times 1760 times 6.9 times 6.9. And I get from that, basically 637,000 joules. Assuming that that's the power, that the power of the engine is all, the energy of the engine has all gone into it, we could say that the power is equal to the work done, 637,000 over, let's say 4.5? No, 4.7. Over 4.7 seconds. And we get a power of around about 135,000 watts, or 135 kilowatts. So the output power of this engine, okay, this is what we call the, so this, because we'll come to efficiency later, this is the sort of the useful output power, is 135 kilowatts. So equivalent to 135 kettles. And that's that calculation. So for the next example, let's stay with a car. Going to be a different car, and let's give it a mass of, let's say, 800 kilograms. And let's say it is traveling at a constant, with a constant velocity of 22 meters per second. And we can say that the force of the engine is, let's say, 2,000 newtons. Now, importantly this time this car is travelling at a constant velocity, which means that the forward force of the engine is being balanced by the resistive forces, also of 2,000 newtons, which is due to sort of the drag forces and friction. So the question here is, well, what's the power in this situation? Like can we work out the power in this situation? Now, to start with, it seems a bit weird to think of power in this. What's the power of this? When because this car is going to travel at a constant speed, there's no gain in kinetic energy. So in this situation here, all of the power of the engine is doing work against, I'm just going to call it friction. So every second, however many joules of energy that engine is supplying, all of it is basically going against friction. Because if you suddenly take your foot off the accelerator and you stop the engine, well, you'll decelerate because of those resistive forces. So can we work out from this, what is the power of the engine in this case? How do we work it out if we've got the force that the engine's applying and we've got the velocity? Well, turns out that we can. So for a vehicle travelling at a constant velocity, the work done is going to equal force times displacement. Okay, so, and the power, given that the power is equal to work done over time, what that leads us to is force times displacement over time. Displacement over time, the rate of change of displacement, is the velocity, which actually gives us force times velocity. And this is a quite nice and important result that we can use if the car isn't accelerating. Because if the car's accelerating, we're also going to get an increase in kinetic energy, which we'd have to account for. But if we're traveling at a constant speed, well, this is what we can use. So in this example, we have, this velocity is 22 meters per second. So that means that this car is going to travel, it's going to move 22 meters 1 second later. So it's going to have, in 1 second later, displacement of 22 meters, applying through that a constant force of 2,000 newtons. So that gives us our result. So in this example, power is equal to 2,000 newtons times 22 meters seconds minus 1, which equals 44,000 watts. 44 kilowatts. Okay. And you can see that you've got Newton and then newtons multiplied by meters per second. You're going to get the same base unit as you do for the standard watt. So that is an example of how you can work out the power of a moving object, even if the engine is not leading to an increase in the kinetic energy of the object. Final thing is to remember that you can actually do these things in reverse. You can always do a thing of the power of brakes. Okay, and it's weird to think of the power of brakes because we kind of think of brakes as being a removal of energy. But, when you brake, you are taking kinetic energy and you're turning it into thermal energy inside the brake pad, and then you're going to radiate it away. So the brakes do work. The brakes are the things that stop you. So let's say the car applies the brakes. I can't spell the word brakes, and I don't know why I crossed that out, but never mind. Let's say we have 8,000 newtons. Okay, so what is, if we apply 8,000 newtons, we can similarly work out various things. So we can say Well, in this case, this is a bit of a fusion. There's multiple ways to go about this. We can say part 1. We can calculate the time to stop. So we can say the acceleration is equal to force over mass. So we had a 800 kilogram car. So 8,000. Oh, excellent. I've done a very, very brilliant one. I've done 8,000. That wasn't even intentional, but never mind. So 8,000 newtons of force over an 800 kilogram car. So we've got 10 meters seconds to the minus 2 is our acceleration. Then we can use A equals V minus U over T. So therefore the time to stop is going to be V minus U, so it's travelling at 22 meters per second. So we say 22 minus 0 over 10, so we stop in 2.2 seconds. And so therefore we can say, well, the power is equal to work done over time. Our work this time is in removing the kinetic energy. So the work in this case is a half times m times v squared. So it's half times mass times velocity squared. So we get a half times 800 times 22 squared, all over this time 2.2 seconds, and multiplying that through, uh, 88,000 watts. And that's the power of the brakes. Even though, you know, we like to think of having a power means that you're speeding up or doing something or going upwards, things like that. Brakes have a power. They are removing thermal energy. They're removing kinetic energy and turning it into the thermal energy at a rate of 88,000 joules every single second. And that is how we can deal with that kind of problem. Excellent. So let's move on to the final thing, just to touch base on, is the second sort of relationship that we're going to talk about here is efficiency. Okay, so this, you might remember, the GCSE sort of equation is that efficiency is equal to useful output over total input. And if you want it as a percentage, you multiply by 100. Now, that output input, they could be power, or they can be the full amount of energy, because power is just energy per second. So they both work in exactly the same way. Efficiency how much energy is usefully transferred compared to the input. Okay, so we can get a measurement of what went out, what went in. And so let's consider, like, where was it, this thing we worked out, this one here, the useful output power of this car, we had 135 kilowatts, was what we got usefully by generating 637,000 joules of kinetic energy. So, an example, the input power of the car in, what question was that? 2? Yeah, question 2. Was 325 kilowatts. What is its efficiency? And for that one, we would just go efficiency is equal to, we had a useful power output, we got 135 kilowatts. Our total input is 325 kilowatts. We don't need to worry about the kilo because there's going to be on the top and the bottom. So you're basically doing 135 over 325, and we get an efficiency of about 42, 0.415, which is basically equal to 42%. So it's about 42% efficient. So that is just a reminder of how we deal with efficiency. So often at the end of these is also a question, these sort of questions as they get longer will be some sort of thing of how efficient the process is. Is it 20% efficient? Is it 15% efficient? Is it 70% efficient? So these are things that you would deal with almost every single time. Okay, so so if we would think a question of where is the missing 58%? Well, in the case of this car and accelerating, what will it have been done? Well, we'll have lost it to various different things. We'll have lost it to work done against drag forces. We'll have lost it to work done against friction. So, and as you get faster and faster, that drag, the air resistance becomes a bigger impact. We will have lost it to, that's friction within, with the tyres itself. We'll have also lost it, to work done against friction in the car itself. Okay, which is one of the reasons why it's important to have well lubricated machines so that we don't have this loss of things as they glide over each other. The output of all of these things ultimately end up as thermal energy in the car or the surroundings. Okay, so all those things, and you might say, oh, but hang on, there's sound, and well, sound arises because of friction, because as things roll over each other, that's how you set up the sound wave. So all these different things is really, it's just work being done against those things. So that's one of the key points about efficiency. So yeah, if you rejoin the chat, we'll do some questions.